Good afternoon, everyone. We're the NASA Xhab team. We were tasked with designing a lightweight tunnel system that will allow for a transfer on the lunar and Martian surface. My name is Tyler Iverson.
Maya Reese.
Will Zavesky.
Tony Corrales.
Madison Walls.
Our faculty advisor is Dr. Todd Letcher. Skipper, and we have 3 underclassmen helping out with this as well. Jeremy Boydell, Hayden DeWitt, and Bryson Love. Our project sponsor for this is NASA. So kind of getting into a little bit of the motivation behind this. So with all the future moon and Mars missions being planned right now, and the infrastructure that we're going to be doing on those surfaces, such as the landers, will be taking up there, the rovers that the astronauts can use to get around, habitat modules that they'll be staying in, or lab modules. Right now, in order for the astronauts to get between all these, they need to put on their spacesuits and enter the outside environment, which is not super safe because it's very cold and there's other hazardous conditions there. So to kind of mitigate this, they need some way to make it so they don't have to enter this environment. So that's kind of where we come in, designing this tunnel that would connect to these 2 different interfaces, allowing the astronauts to not need their spacesuits and just walk from one to the other.
Yeah, so our design here is very similar to if you were to go to an airport, you've definitely seen a jetway. And we want to basically bring that onto the surface of the moon and Mars. In that case, the astronauts will not need to leave the habitat or the rover without the need of space.
The main goal of this project is to create a lightweight actuation mechanism to align to different connection points on, like, let's say, rovers or habitats and things of that nature. So it must be lightweight, articulated, actable, pressurized, so astronauts don't need to put on their EVA suits when going from point A to point B. It also has to easily traverse both the moon and Mars and autonomously align to different connection points. For the prototype, we seek to validate the lightweight articulation mechanism as well as the autonomous alignment and connection.
Getting into some of the state of the art, inflatables have been around for many, many years, since long before NASA. The reason we do this is because the weight and mass that's involved from putting infrastructure into Mars, it really does become a drag and really expensive. So to combat this, in 1952, Dr. Werner von Braun had the first idea for inflatable habitat. This really didn't go anywhere, especially as the Apollo 14 missions. They usually just left it in the air for a while. Spiked it until 1998, 1997 to 1998. The Xhab project was the first milestone in the inflatables projects, where they basically validated that, hey, we could compact a lightweight inflatable module for space and inflate it in 0 G. They then moved to leak for burst testing in 2012, basically proving that it would leak rather than burst, because if it leaks, you can fix it. If it bursts, everybody dies. And then in 2014, because this project was such a success, they proved that it leaked rather than burst. They wanted to see what it would do when it burst. So they pressurized it to about 4 or 5 times what they expected it to burst at, and it held solid. This was good, and eventually it did burst, proving a successful mission. And that's where NASA took a step back and decided, hey, let's get some companies and schools involved. So from here on out, the inflatable modules went directly to schools such as us. And an example of a company that took priority in 2016, Bigelow sent up the expandable activity module, where it is still in operation today.
Now, taking a look at some of the state-of-the-art concepts for tunnels that exist. We'll mention that we're kind of mirroring an airport jet bridge, and so here are some of the ways that NASA has already done that. So the top left image there kind of shows the connection mechanism, the mechanism that is used on the outer shell of the tunnel to maintain pressure so that there's a safe environment for the astronauts to pass through. And there's also a mechanism that allows for the orientation of the connection surface. And so right up here, you can see there's a bunch of linear actuators connected between 2 rings. These allow for 6 degrees of freedom. Basically what that means is you control that end surface in basically every way, which allows for really fine adjustment. However, the Stewart platform is pretty darn heavy, so that's a way in which we're trying to mitigate mass in this project is by finding an alternative to that. And we'll talk about that a little bit later. In the bottom left here, this is an image that was posted in a NASA article written partially by one of our sponsors, actually. And this is showing how tunnel for lunar and Martian purposes needs to be collapsible. Volume is a huge thing when it comes to how much it costs to send stuff up into space, as well as mass. So being collapsible is very, very important. And this, what you're seeing here, is specifically the restraint layer of the soft good material used to wrap the tunnel in to protect it from radiation, micrometeoroids, and a bunch of other stuff. And then on the right there, this is another photo from an article written partially by our sponsors. And involves the NASA Chariot rover and a concept tunnel that they built in their lab. And as you can see, there's really no high expensive materials here. It's pretty simple. And so this is something that's encouraging for us as we go about designing our own prototype, because we don't have the funds that NASA has. And we're just figuring it out as we go. So these are all just 3 things that we're keeping in our minds as we go about designing our system. So now looking at some design matrices, and to preface, our decision-making process has been delayed pretty heavily due to the government shutdown recently. That delayed us a lot, and it kept us from making a lot of really important decisions that maybe some of you have made. So we're still kind of working on what we're going to choose. But here you can see how we've laid out what we've determined to be our best actuation design for our system, for actuating the tunnel. And over here on the left, you can see how we weighted those decisions. And our 3 biggest things that we took into consideration was the actuation method's ability to be scalable, its weight or mass, and its precision and accuracy. So as we mentioned, Stewart platform, very precise, very heavy. So we'll talk a little bit more about how we rated things like the Stewart platform in our consideration.
Yeah, so some of the components we considered was using the Stewart platform. And for this, we determined that it was very heavy. It was also very accurate at, or precise with the actual actuation compared to the other methods. In addition to that, it's also not quite as scalable. Then another thing we considered was the position of the actuators. So we looked at positioning the actuators towards the end of the tunnel versus having them more in the center. So with the end tunnel actuators on the ends, it is a lot more scalable, as you don't need to scale it based off the design of the tunnel. You also have more accuracy as you're moving less the components, and it's also a lot lighter because you don't need as much to move it. And then on the ends or in the center, it's a lot heavier. You'll have more that you'll have to move. It's also less accurate, again, because you're not as close to the actual interface. And then it is all. And then for the driving base was our next consideration. This was the heaviest of the options. And it's not as accurate compared to the others, as you are going over unknown terrain. So you get less control over it. And then it is also it's heavier as well. And then for the scissor lift consideration, this one is a lot more scalable than some of the others, as you just basically have to add more links. This is for our vertical adjustment. And then on this, it also has a relatively low mass compared to some of the others, because you only need the mechanism to drive it, and then you don't need to have as much in terms of the rest of the actuations. And then for the mass, again, it is pretty low. And then it's also fairly accurate, as there is only one input, so you don't need to control too many directions. And then for the winches and pulleys, this was very lightweight, as you don't have all the systems connected, and you're able to just drive it with just a single winch. And then with this, it's also not quite as accurate if you were to have linear actuators on the Stewart platform, just because you don't have as much this, or you have a little bit there. And then for the scalability, it's pretty scalable. All you really have to do is increase the length of the pulleys.
Looking at some of these design choices that we were making, we came up with a couple design iterations that we're looking at. This is the first one here. It uses a driving base to handle the bulk of the alignment. And so over, we kind of tow this system over to where you want to connect it, and driving base with power on position its first connection end that you can see on the right there, fairly close to the connection point, and those actuators on the end would handle that final precise movement that is needed for the connection there. And then the driving base would drive out towards the second connection point and the second connection that you see on that right picture. Then also have its actuators perform the final articulation there. And so this left picture kind of shows it in its most compact state, where it has about a length of 5 feet, and then on the right, it increases all the way up to 15 feet, kind of really enhancing that scalability. One thing about this is it's a fairly large system, doesn't really seem lightweight, but it'll offer a lot more capabilities to be able to perform in any potential mission scenario. And so kind of going with our first semester testing here, we wanted to kind of look at the autonomous alignment of this driving base. So this is a real that was built last year that uses a Raspberry Pi or drive wheel system. And if we would do a driving base, we would basically be doing the same exact thing. So that webcam that you are seeing on the top of the rover on the right side is getting that footage on the left. So it's reading this April tag, essentially a QR code, generating its position relative to it, and sending commands to the rover, which is controlling wheels, to then align itself to that tag. And then ask them to talk about some more of the elevation here.
One of the main things we were looking into for this project is doing a sensor lift. So our first semester testing was 3D printing a small scale sensor lift. And we did this in two main configurations. The first one used a linear actuator, is actually the video that's on the right over there. And as you can see, this worked out very well. The second one was a rack and pin. Fortunately, the stepper motor for this one had insufficient torque, so it wasn't really able to flip the mechanism, but it still provided some valuable feedback for us. In addition to this, we also did structural testing, and for this, we used titanium 6-4. So we had 12 cross members with 7 connecting rods. We applied an 800-pound force at the top, and we found that there's a factor of safety with this of 2.56. And in addition to this, we looked at the stress concentrations and we changed up the geometry to provide a little more strength. We simulated under the same conditions. We found a factor of safety of 3.86 while only adding an extra 2 pounds of mass.
Take a look at the second design iteration that we came up with. Kind of what Will was talking about earlier with the inflatable tube actuation system. One way to implement that we found would be in specifically the egress of the tunnel. And so the tunnel itself, we thought about actuating with inflatable tubes. However, we also thought about specifically isolating the end of the tunnel as its own mechanism in order to finally adjust the placement of that connection ring using pressurized tubes. And you can see that here in the bottom left and the bottom center image. Basically, these tubes, I think there's 8 of them here, they're arranged kind of like a Stewart platform. So instead of having heavy electrical, mechanical actuators, we're replacing each of those with a tube that inflates lengthwise. And that's basically replacing all that heavy actuation with pressurized gas. And so we should be able, we use solenoid and microcontroller arrangement to control that connection ring in the same way as a Stewart platform, but with a whole lot less mass, and we would make this collapsible also. And given that we actually had our SDR yesterday, this is one of the things that NASA was really interested in. This inflatable idea, inflatable actuation, because they haven't really ever seen that before. And so this is something that will be a large focus of our project moving forward. In the bottom right-hand video there, you can kind of see the idea of how we want that end ring to be manipulated by an inflatable material. Just kind of being able to control it in a whole bunch of different dimensions. So that's kind of how that works. So looking at our Gantt chart from this past semester, like I said, we were pretty heavily delayed by the government shutdown, but we were able to kind of start testing for a bunch of potential options for our actuation system, materials, and whatnot. So we've been doing a lot of first semester testing, a lot of design matrices, and a lot of modeling and concept drawings for that stuff. And like I said, our systems definition review was yesterday, and we might have our PDR by the end of this semester. We might not. NASA scheduling is, and our scheduling is kind of hard to align. So we'll do our best, but if not, We'll move to the second semester Gantt chart, where we would start right off with our PDR and hit the ground running. And then following that, we would have all of the other NASA and senior design milestones that follow that until the end of the year.
And for our budget, there are three main things that we want to budget for. The first will be for the prototype of the actual tunnel itself. And then after that, we'll also be budgeting towards a hatch prototype. And then we'll also have the budget included for going to actually go down to the Johnson Space Center to present to NASA. And then for the prototype tunnel material, we estimate a cost of about $5,700. For the actual electronics, for that, about $3,500. And then for the prototype hatches for material, about $1,250. And then for the electronics, about $250 for that. And then to travel to the Johnson Space Center, $4,300. And then for any extra overhead and indirect costs, I know SDSU takes part of the money that we'll get, so that'll be about $5,000, and that'll give us a total of about $20,000.
Overall, conceptually, we're going to design a system that prioritizes lightweight that can be operable on both the Moon and Mars. If you need to perform some sort of harness articulation to any of the different interfaces that will be there. And next semester, we will be building a prototype that will seek to kind of validate whatever we choose for our actuation method, as long as whatever control software is needed to make this work. Now I'll open up to questions.
What is the size of your prototype? Scale of your prototype?
That's kind of on the side right now. It kind of depends on what we think we do with money wise. We want to spend a lot of money on materials and make it as large as we can, but our electronics might not be as great. It'll probably depend on if we would go with something that's more electrical, like having a lot of actuators, or if we go with a lot of inflatable tubes and stuff like that.
We'd like to make it as large as possible too, so that's kind of, we're trying to weigh out how big the camera is.
Well, we just had the SDR yesterday and really only have been able to talk to our NASA sponsors a couple of times because of the government shutdown. So maybe tell people about who is on the committee from NASA and what their day jobs are, what they do commonly at NASA.
Yeah, so a lot of engineers who are kind of specializing in like the soft skills area, kind of looking at the inflatables and how to use that. So I think that kind of really made them interested in our inflatable idea. Because right now the soft skills are kind of just used to like shield outside the tunnel, or they've kind of been using them, not actually performing that actuation. We kind of suggested.
What's your main sponsor? No. But Rock.
Right. We were to the south, so.
Yeah. In his connection to South Dakota.
Oh, I guess he's from Mitchell. So
Yeah.
he's from Mitchell and now works down at Johnson Space Center on this kind of stuff.
Can you explain a little bit? So the inflatable on the end, is that sealing with what you're attaching to? Or can you explain this a little bit more?
Yeah, so this ring, this is a pretty rough CAD model, but ideally this ring would have some sort of capture mechanism that would attach to the lunar module, that would attach to the rover or the habitat. And then that would be manipulated or motivated by those inflatable actuators. So these are providing alignment so that it can actually make that connection. And yes, it would be C.
What do you think your biggest challenge is going to be in actually building the prototype for this?
Well, the goal of the inflatables, probably designing tubes to be able to perform the actuation we want. It's not really any off-the-shelf options there. So when we were talking with them about how we should go about prototyping this, they kind of said they're looking like probably nylon or vinyl, essentially like what bouncy houses are made out of. And they actually suggested going to like the school of fashion here, talking about sewing and stitching, and how to put this kind of thing together to be able to complete how we want it to. But it's kind of hard to like, before to visualize it, which none of us have. So we do the inflatables, that'll be pretty big learning curve. Otherwise, it'll just be like reverse kinematics of the line.
With some of the designs that you've like showed, a lot of them look more rectangular. Have you considered making this more of a rectangular inflatable, or is circular more what's going to work best? Have you guys looked into that at all?
You know, that's something we don't really have a good answer for. I think I kind of went to default to circular because that's more of what NASA's already done, and I'm kind of trusting their experience on that. However, that's something that we would have to be open to as we potentially work with the fashion department. And I mean, I don't really know how that stuff needs to work when it is inflated. This model in the center here, that's just atmospheric pressure. I don't really know exactly what pressure we're going to end up inflating each of these different tubes to, or the inflatable material in between them. I guess that's something that will have to be an area of further study.
How do you plan to have people and cargo move through the tunnel?
Right now, we probably some sort of walkway through that. One thing that's kind of standard with this is the like door here is 40 by 60 inches, which we actually found out too. This door will probably be elevated off of that surface a little bit. And so right now, like an astronaut, we just have to just walk through it, step over that, whatever. Cargo wise, we'll probably need to find a smoother way for that to move through, but they haven't really thought about that until I said.
You have a plan for your like habitat to go around that walkway while still being able to make contact with the ground there, or?
What were you saying? Like that's gonna be
Yeah, 'cause you're gonna be going around the door and you have
Yeah,
that
so, like,
on.
kind of connecting this to this would be kind of soft goods layer that we talked about before, like this. That's really like extend out. Then when it's already extended, then that would inflate, provide the shield. Around these points here, they'll probably have more of something that they call like dust socks, which is just kind of like a really nice tarp that covers that up, to protect it from like the moon dust, stuff like that.
How are you guys planning on equalizing the pressure between the modules and the walkway?
I think that we've been looking at a couple NASA state-of-the-art concepts for kind of this surface here, and this bulkhead would actually have lines for, I think, gas, power, and data. So those three resources would be transferred through the tunnel and would also feed the tunnel. So any gas supply that we would need would come from the habitat like they were on ice.
Is your guys' design for transferring between habitats just for habitats that are on the same plane? Or could you say you have a habitat and an elevated plane and a rover on a lower position? You could transfer between those.
So in this concept right here, this walkway can slide back and forth like you're pulling or on your dresser. And then right here and actually right here, it can like rotate. So these can be at different heights. And then this here also has an axis of rotation like that. So they can even be like offset as well and at different heights.
Okay.
So still be able to account for that.
So you can also turn it and also adjust elevation with it. Okay.
Okay, we have one more quick question.